We want to talk about scaling the vertical axis for a sine function. Now I didn't draw these circles freehand. No way I could have made them look good freehand. Might get one good circle freehand, but I'm not going to get three concentric circles freehand. Okay, and I probably won't even get one. Okay, well anyhow, the red circle you see here we take to be a unit circle, meaning that it has a radius of 1. Now the arc around the complete circle has what length? Well, you should know, but the ratio of circumference to diameter, and the circumference of course is the arc corresponding to the complete circle. The radius of circumference to diameter is pi. The diameter of a unit circle, which has a radius of 1, is 2, so the arc distance around the complete circle is 2 pi. So we say, okay, well, we're going to identify the central angle around the complete circle, and I'll indicate that angle here. Okay, this is the central angle for rotation around the complete circle, and that's going to be identified with the arc distance around the complete circle on the unit circle. So that arc distance is 2 pi. Now we sometimes call that 2 pi radians. I'm just going to call it 2 pi because radians is the default unit for angle, and if we want to talk about the angle of 2 pi, that automatically means 2 pi radians. If for some reason we wanted this to stand for 2 pi degrees, we would have to put the symbol for degrees or write the word degrees next to the angle. We'd have to specify the units. We can give the angle with unspecified units as long as we understand that that angle is then in radians. Okay, so central angle for the complete circle is 2 pi radians, or just 2 pi. Now, if I subdivide the arc between the point where the circle intercepts the positive x and the positive y axes, we get, well, half of that arc. And of course, that entire arc is 1/4 of the arc of the complete circle. Half of that arc is therefore 1/8 of the complete circle. So the arc distance is 1/8 of 2 pi, or pi over 4. So we're going to call this angle pi over 4. Or if we prefer, pi over 4 radians. So I can write, or if we want to really be specific about the angle, as we often do, we could write that pi over 4 radians. Okay, so the angle corresponding to an arc on any circle is the arc distance that you would travel around a unit circle to complete that arc. Okay. Now, this means that this pi over 4 radian angle applies to this smaller circle, to the to this angle here. I mean, the pi over 4 radians is now a property of this angle. So it would be the angle at which the arc of the smaller circle intercepts this line, or the angle at which the larger circle intercepts this line. The angle is pi over 4 no matter how big the circle. Okay, well, over here I've sketched a graph of the sine function corresponding to the unit circle. This is a unit circle. This point projects straight over to the point on the y-axis where y equals -1. This point projects over to the point where y equals 1. The sine function comes up to a peak at 1, down to a valley at y equals -1. Y equals 1 here, y equals -1 here. And the basic sine function completes a cycle as we move all the way around the circle. Now, we don't have to label any of these angles. Okay, this sine function could be completely unlabeled, but once we declare that this is a unit circle, the y goes from -1 to 1. And also, if we want the horizontal axis to represent the angle then has to go from 0 to 2 pi, because to get this complete cycle, we have to go exactly once around the circle. And this, as we've seen before, gives us the function y equals sine of theta. Now, if we wanted to sketch the graph for this bigger circle, okay, we would get a graph of a sine function. It wouldn't be the function y equals sine of theta, but it would be a sine function. And remember, when we construct the graph, we consider it to be unlabeled. So here is didn't do real well on that one. That's a little too pointy, but you get the idea. Here would be a graph corresponding to the bigger circle. Okay, and we could also draw a graph corresponding to the smaller circle. Now I've marked the points where the bigger circle projects over, where the y-intercepts of the bigger circle project, and also the points where the y-coordinates of the smaller circle project. So I could also draw a curve representing the sine function we would get if we used the smaller circle. Both of these graphs can be considered unlabeled, but now that we have a unit circle here, we know what our unit quantity is. We can see that, well, okay, this quantity here is about, it actually looks like about 1.7. I wrote 1.6 here. On a scale where this is 1, I believe this would come out around 1.7. So I'm actually going to change that and say that the radius of this bigger circle then has to be 1.7. And the smaller circle, it looks like we do the smaller circle and come up to here, it's pretty close to half. It might be 0.6 on the scale dictated by our unit circle. So I'm going to say that this point here is where y equals 1.7. I'm going to use the 0.5 here, and negative 0.5 here, and negative 1.7 here. Okay, now look at first at the function at the curve that we get from the smaller circle. We see that this point is half as high as this point, and actually if we go out to the angle pi over 4, the y-coordinate at this point will have to be half of the y-coordinate at this point. Prove that geometrically. You have similar triangles. One triangle has twice the hypotenuse of the other, since the hypotenuse is equal to the radius, so that the y-coordinates will be in the same ratio. And the ratio being of the hypotenuse being 2 to 1, the ratio of the y-coordinates at this point, at the point where this line intersects the two circles, will be in the ratio of 2 to 1. That's going to be the case anywhere. Okay, we draw any line out here. It's going to have a certain arc on the unit circle, so it's going to have a certain angle in radians. And no matter where I draw that line, any radial line from the center, the y-coordinate that we get for the unit circle will be double the y-coordinate we get for the smaller circle. Meaning, of course, that each of the points in this graph, on the red graph, is twice as high as the corresponding point on the lower white graph. Well, in that case, we can say that this graph here is the graph of y equals 0.5 times the sine of theta. Okay? Because sine of theta is the y-coordinate corresponding to the theta coordinate on the red graph. The white graph is half as high, so the y-coordinate has to be half as high at the same value of theta. Okay, going to get half the y-coordinate on this graph that you would get on this graph for any given value of theta, and that totally corresponds to what we just talked about. Similarly, the y-coordinates on the other graph that's drawn in white would have to be 1.7 times the sine of theta. I'll put parentheses around the theta here. I didn't put parentheses around the theta here because I didn't have room. And the parentheses are really unnecessary in writing this function, but I like to use the parentheses most of the time. Okay, so that anytime we have a graph of a sine function, so we can have any unscaled graph of a sine function. And I didn't, my x-axis isn't consistently labeled here, but or my horizontal axis. Okay, we can scale it by simply saying that this number up here, let's call it A, and the y-coordinate down here is negative A. So if this distance is 2 pi corresponding to the angular displacement all the way around the circle, this would be a graph of y equals A sine of theta. Now, I did have a note down here, and I will draw your attention to it, that if we have one cycle of any sine function, then that sine function had to be generated, or could have been generated, by a corresponding reference circle. And one complete cycle around the reference circle corresponds in a way that's very obvious to one complete cycle of the sine function. So that I'll say delta phase equals 2 pi. The change in the phase is 2 pi between here and here. Now, what I mean by phase, the phase is the angle on your reference circle. Okay, so phase is the angle on the reference circle. Very important idea that we want to keep in mind as we go on and talk about scaling the horizontal axis.